Okay.
Okay, thank you. Okay, so yeah, so the work I'm presenting is today is really an effort that we do at Environ Canada since maybe a couple of years in the hope of improving our sales informations in higher resolution forecast products that we are producing. So this is really a teamwork, a team effort with everybody listed here. Some from Environment and Climate Change Canada, others from McGill University. And so to put in context, so at Environment Canada, we are operating a number of ice ocean prediction systems. So they are of different resolution in different regions. And these are all fully coupled NEMO-SAIS models. We're using SAIS 4. We are in the process almost finished migrating with SAIS 6. And it's forced from an atmosphere from the Global Deterministic Forecast System. And how it works is basically we have a global model at lower resolution, so the GIOPS, Global Ice Ocean Prediction System, that is 1/4 of a degree. And in this, we have embedded in this original model for the Arctic that we call the RIOPS, and that you may have heard in other presentations. So this is, again, ice ocean. You have the sea ice from SAIS, and this is at 1/12 of a degree. And in RIOPS, we have embedded a few coastal prediction systems, so CIOPS, coastal ice ocean prediction systems, that are running at 1/36 of a degree. And so as you can imagine, in the global GIOPS, for instance, you don't necessarily expect to resolve very small fracture, sea ice fracture properties, for instance. But as you go to higher resolution, the question comes like, how much should we resolve them and how to resolve them? And we are also working on our questioning whether we are going into a RIOPS at 1/36 of a degree, so that you don't have necessarily to have as many systems to deal with. And so another thing that has been mentioned yesterday by Elizabeth and I think Ed Cameo is that the end users that are using these products often want, what they need is often at a resolution at a scale that we don't resolve in the model. So a lot of the work that we've done in the last few years is really trying to find ways to convey information that is useful to them based on model forecasts that are not at this resolution. So if you think about the few things that you can do to get this information, so I basically have these 3 points here. So you can, for instance, parameterize subgrid processes so that you take from that you input in a model, so you're not resolving, but you're including the processes in the model physics. You can downscale the information that you get at this coarse resolution and find ways to find out what does it mean for local scales. Or you can modify basically the size dynamics as you go to higher resolution. You can make sure that you have everything that you need to start resolving these small scale processes. And a lot of the work that we've done in the last few years fall in mostly in the two first categories. So for instance, Elizabeth mentioned the ice grounding parameterization by Jean-François a few years ago. So this is really something that you don't resolve, but you parameterize this grounding of ice fields, and then you're able to produce landmass ice. Recently, we've done a paper by Dupont et al. 2022, where they updated this grounding parameterization for that is maybe a bit geometric to a more of a probabilistic approach that yields similar results, but have more of a physical sense if one or more realistic. Another thing that's been done is to produce pressure forecasts. So this also has been mentioned by Elizabeth yesterday. So from the model simulation, you basically send predictions of the sea ice pressure, and that's, I think, useful for navigators. But what we also try to do, or like the ongoing work with that, is to try to find ways of downscaling this pressure that you have at the maybe kilometer scale model grid and try to make from very high, like meter scale simulations, you try to find how does that larger scale pressure would mean for a boat, say, that is navigating through this pressure ice. So this is just basically a playground that you do, but the idea is eventually to get downscale information from the RIOPS. But for this talk, basically, as we are looking maybe for a 1/36 of a degree RIOPS, then we want to look at the CI dynamic that is produced by the model, and we want to improve that. And this is really following the CIREX experiments that Niels is going to present later today. So what I mean there is that if you look here, a simulation from the RIOPS, so we have here the ice thickness at the top left, the CI concentration at the right, and you have the divergence and shear deformations at the bottom. And we do see that in the RIOPS, we do have these nice lines of deformation, so these linear kinematic features where the deformations are reorganized in lines. So this is encouraging, but if you look at modest observations, so this is brightness temperature imagery taken from WorldView. So in these images, basically you see the leads from the bright colors that shows warmer temperature. And you can see also thicker flows that are in dark purple where the ice surface is colder. And we see that, well, in areas you do have the overall dynamics, right? We have an opening event. So this is in Beaufort Sea. You have the Alaska coastline here, the Canadian archipelago down here. And so we do have kind of encouraging dynamics. But then when you look at the number of leads and the size of the ice flows, RIOPS has very big ice flows, basically, and too few of these lines. So our goal is basically to find ways to improve that. And so in this project, basically, we want to improve that by attacking maybe 3 fronts. So the first one is, again, a kind of a post-CIREX thing is to test different parameters that we have. So in CICE, we use the EVP model. And so we have a number of dynamical parameters that you can try to see if we can tune them to improve our deformation statistics. And this is, I guess, the first step for us to do, because as a forecast, an operational forecast institution, if you want to change things in our model, we need to demonstrate that you're improving scores and you're not degrading anything. So I think it's simpler to just play with what we have, and then it's easier than to implement completely new things. And so what it means, playing with it's basically playing with the ellipse. So that's the first step that we do. So it's been done by Amélie Bouchard in 2017. So Bruno just presented this. You change the ellipse, and you can change the formation. So what is this? Is that so the EVP is basically an approximation in the viscosplastic rheology where the deformation is determined by an ellipse that sets the maximum stress that the ice is able to sustain. So basically, in this you have the x-axis is the normal stress. So divergence in the positive, convergence in the negative, and you have shear stresses in the y-axis. And if your stress is low, you're inside, then this is an approximation, but basically you have a very small deformation that are simulated as a very, very slow strip. So, but it's so small that you virtually can imagine this is a rigid body behavior, and this is what happens inside of these big flows there. But when you reach the ellipse, you're breaking, and that's where the plastic laws come in, and you have this plastic flow rule, the normal flow rule, which basically just tells you, depending on where you are reaching the ellipse, the deformation that you're going to get, the type of deformation, and is determined by the normal to the ellipse. So if you're pointing, if the normal, you're on the top of the curve, the arrow is pointing up in pure shear, then you're going to have pure shear lines, and this is what you see in these lines where you have very low divergence or convergence, but you have high shear. But if you more in the two sides of the ellipse, then you're going to have pure tension, pure lead opening, or pure ridging. And if you're in the middle, in the between, you're going to have a combination of both. So from that, when you change the size of the ellipse, then you're basically changing how the type of deformation you're gonna get associated to the same state. And so what we did is that we ran many re-up simulations by varying the ellipse. So we have 4 different ellipse ratios, so basically flattening the ellipse while keeping the P star constant, the maximum compression constant. And we also test 3 different composite strengths. So this is basically the length of the ellipse, and a combination of these 3 ellipse ratios and 3 composite strengths. So we have a total of 12 simulations. And then from these, we analyze the deformation statistics. This is still preliminary. We yet have to implement a few diagnostics from the star experiments, like the temporal scaling or the LKF detection and tracking algorithm. So this is still part of future works. But for now, oh yeah, another thing, because we have many simulations, one thing that we did to basically make sure that we're comparing apples and apples is that we each simulation are optimized for the drift against the buoy data from the International Arctic Buoy Program. So we can see here that they all have very similar biases. And so if I look at the PDFs, so this is the PDFs of all the 12 simulations. So they're pretty much clumped together, but you can see that each color indicate different ellipse ratios. So red is a standard ellipse ratio of 2. Going to black is a 1.25 ellipse ratio. And you have different lines, types of lines that are for different P stars for each ellipse ratios. And what we see is that changing the P star doesn't affect much. They all line up together, but changing the ellipse ratio does make a change. And you can see that what happens is that as you decrease the ellipse ratio, so this is basically increasing the shear strength, you basically have a higher number of deformation and a high deformation. So BF basically tells you how many points have high deformation versus points that have smaller deformation. So this means that as we increase the shear strength, we have more deformation. This is similar with what Amélie demonstrated. And when you look at the spatial scaling, so Bruno again told a bit what this is. So basically you start with basically the nominal scale, you make an average of your deformation in your field, and then you basically coarse grain your deformation, repeat the experiment for larger scales of deformations, and then you get different values. And we see here that again, P star, like changing the P star, the composite strength doesn't have much of an effect. But changing the ellipse ratio had a really, like decreasing the ellipse ratio really improves the scaling properties. And so in Bouchat and Raut 2017, they say basically you can decrease the strength or increase the shear strength to have better localization. What we see here is that the shear strength is really much more impactful on these things. And what it means if you want to have a visual picture of that. So this is a monthly mean deformation in the Arctic for different simulations. So you have here the standard ellipse ratio of 2, and here at the top right you have when you have a ellipse ratio of 1.5, and see you have many more deformation lines with that. But I want to point out that it's still, I think, fewer than what we should expect in the Arctic. So I think this is not, this is not all of the answer. We think we still more work to do, I think. And I think that I find interesting. So basically, this scaling is made for 3 months of data. So we have 3-hourly outputs, and you repeat the scaling and you accumulate that, and this is for 3 months. But you can do that for each 3-hourly snapshots, and you would get a distribution of this slope, of the scaling slope. And when you do that, so you do see that from ellipse ratio of 2 to an ellipse ratio of 1.5, you have basically an increasing slope, but you also have a widening of the distribution. So this is something that I find interesting. I'm not sure what it means yet. Like it's just something I find interesting and we need to investigate. But yeah, I just wanted to put that up there. So the other 2 fronts. So number 2, try other model developments to represent smaller scale physics. And so this is more longer term, and this is basically an interest that I have personally, because I did my PhD on the damage parameterization, and I think it's important if you want to see if we should implement that, for instance, in our forecast products, then we should investigate really the behavior of this model. So I have a poster where I'm going to talk about this, and this poster basically producing very idealized experiments with both the VP model and the MEB and investigate how the ice reacts in different regimes. So feel free to come and chat about that. And finally, develop capability to assess the quality of our study formations, because often when we talked about the formation, we compare about RGPS that ends in 2008. And so we have not a lot of data for recent years. So what we're doing, we're preparing a CIS deformation product from the Sentinel-1 and RADARSAT constellation mission. So this is from the ice tracker algorithm from Howell et al. In 2022. This has just been published. So basically, they use they track features in pair of images, and they have a data set of CIS motion, and they are sending us this data set, and we're processing that to infer the CIS deformation for that data set. And so this is kind of coverage we can get for now. So this is for March 31st, 2020. You can see you have many gaps, but it's for 1 day. So this is quite a good coverage, and it's also covering a much wider region of the Arctic than RGPS. So this is in progress, and we're also hoping to have even more basically resolution for 2022 onwards. So we're preparing for now from 2017 up to 2021. And yeah, so that's it for me. So this is a summary of things. I'm not going to go into this, but I wanted to put some questions that I personally have when we talk about going into a high resolution. Maybe not everyone's going to agree with that, but this is really my things that are bugging me. So the first one is numerical accuracy. So we often talk about numerical convergence of CIS models. But as we go in finer scale fracture physics, we often talk about elasticity or basically parameters that are integrating the errors at a high time resolution, and which may become a problem, or is it? It's a question that I have, and how much should we care? Like if especially also in the smaller scale, we tend to talk about including heterogeneity. So should we count this numerical things as part of the heterogeneity? So this is a question I have, and I have no answer to that. I think this is something we could investigate. Also, we are using continuum models in increasingly high resolution, and so as we get to flow resolving territory, is it okay, or what's the limitation of that? I think I'm not sure if this is answered. If somebody has the answer, I'd be glad to hear it. I think I'd like to know what are these limitations, and also the choice of rheology. So this is maybe for in terms of forecast, maybe, or like what we have our prediction systems. But as we're increasing the data assimilation and the frequency of it, how much does having a rheology, is it the main thing? With different rheology produce different things if you assimilate CIS deformation and ice thickness at a given frequency. So maybe it is, but I think it's a question. These questions basically. The answers to this question, I think, would guide future model developments for predictions, in my opinion. So yeah, that's it.
Yeah, thank you for the very compact and precise talk. We have plenty of time for questions or also for answers to these questions, if you wish so. Yeah.
Thank you for your talk, Mathieu. I was just wondering on this slide, so I understand you're looking at stuff at high resolution.
Yeah, I don't hear
even if
from
the
here.
okay. So you're looking at stuff at very high resolution, but I'm just wondering, you're doing spatial scaling, but it's based only on one order of magnitude in your spatial scale. I understand that well.
Yes, and so this
Okay.
is, again, this is preliminary results.
Okay.
I'm not, in this spot, I'm not showing, like, so our nominal scale at the RIAPS is 4 kilometers.
Yeah.
And so the way we did it, I have maybe, yeah, across maybe 2 or 3 magnitudes. I don't show the full things, but yeah, this is something we want to increase.
Okay.
So,
okay.
and we do see, I don't show the nominal scale because I think with the RIAPS, it's a question I think we have on whether the scaling at the nominal scale, like there's a point, like if we want to reproduce gradients, then maybe the scaling will not go until the very nominal scale. So this is something I think that
Okay, because you need a couple of grid cells to represent the gradient.
Sorry?
Right? You don't want to go to the nominal scale because you need a couple of grid cells to represent the gradient. So,
yeah,
okay.
I think
yeah.
we are, and I think that's the case with any continuum models. Basically, you're solving for gradients that you need a couple of grid cells to resolve. So, yeah.
Okay. Mathieu, you said at the beginning that there was some 136 parts of the model as well, but
Yeah.
you were also only talking about 112 later. So I was wondering if you looked at CIs in the 136th bits, and like if it's like if you got eddies, how they can affect the fracture of the CIs. Now, if you looked at such things.
That would be very interesting. I'm going all the way to the beginning, I guess. Yeah, so these are the CIAPs. No, I haven't looked at the properties in there. Like and you have, like, for instance, this is the West Coast, so there's no CIs there. So we have some in the Gulf Stream, but I'm not sure if this would be like, I'm not sure how much this would be a right setup to look at this, because, you know, this is very seasonal CIs and it's just quite small. But yeah, it could be interesting to see, yeah, we could try to find ways to investigate, yeah, this type of information at these scales. But I think often when we look at these, we look at the pack ice in Arctic, for instance, and this is we don't have that at 136.
Yeah, so I was in the project and we've been looking at different rheologies and different resolutions as well. And so I did run a 136, but only sea ice, so no ocean. Actually, we did see if you do increase the resolution of your model, you get much more, like more fractures, but or more localized fractures. So if you can go to the high resolution, it is also a good way to solve your problems rather than fiddling with the parameters. And also, what you see, if you use EAP instead of EVP, you also get much more fractures, but also the angles there become the diamonds instead of these squares. So maybe you can try, maybe.
Yeah.
Okay, in your sensitivity studies, you were showing tests on P-star, which means that you're using the Hibbeler strength, which is kind of an average over all the categories in the thickness distribution.
Yes.
But there's another option that depends on the thickness distribution. I wonder if you tried that and whether that affects the fracturing characteristics.
I haven't looked at that. I'm actually not sure which strength we're using, which parameterization. So. Yeah, no, that was thinking about something. Yeah, sure. I think, yeah, there's many other things that we should try, and yeah, going into this, and yeah, definitely, but no, we haven't.
Sorry. I was just saying that Amélie and Cyrex One looked at the MITGCM where they use ROT-ROC and the P-star closing scheme. So I couldn't answer your question, but in the Cyrex One, I think you're going to find your answer, figure 7 and 8.
We have time for 1 or 2 more questions.
Thanks for a lovely talk. Yeah, okay, I can echo what Stephanie said about the increased resolution. Increasing resolution definitely gives rise to more deformation, but that's probably not a surprise to you. Okay, and we found that in the EAP model as well, and as well as the EBP and almost any model actually. Okay, but actually I was going to this last question you threw out to the community about the limits of continuum modeling. Okay, I mean I've been banging on about this for at least a decade, more like 20 years. No one knows, to my knowledge. Okay. I have a PhD student starting next week, so maybe we'll get a solution to that okay. in about 10 years' time, perhaps. But if anyone else is interested in this question, I'd be interested to talk to them, given that we've got the student just starting, okay, who will probably be taking a mixture of continuum and discrete element modeling approaches, trying to address this question.
Okay, yeah, thank you very much. We have one more talk before the lunch break. This is also quite related to the previous two. Talk given by Damien.